Okay, we're going to start. Thank you everyone to be here for that general seminar. It's my pleasure to introduce Dr. Preethi Rajendram Soundararajan. She graduated from IT Madras, then did a few years in industry, did a PhD in Centrale Supélec, so in Paris. She speaks French a bit, so do not hesitate. And then a postdoc in Cambridge, that's where we met, and now she's a lecturer in the Department of Aeronautics and Astronautics at the University of Southampton. And Preethi, the floor is yours.
Thank you, Kamta. I can't speak French, but I've stayed in the UK for 3.5 years, so it has gotten a bit rough. But anyway, okay, so today what I'm going to talk about is decarbonizing combustion in the context of aircraft engines. Okay, and in particular, I'm going to talk about this phenomenon of thermoacoustic instabilities and why it's one of the biggest challenges that the industry is facing as we transition towards decarbonizing combustion. So I thought I'll start light, but Kanta already revealed it. So to all those people outside Paris, I tell them that I lived in Paris for nearly 3.5, 4 years, but to this crowd, I can't say this because you're all true Parisians. So I did my PhD from 2019 to 2022 at Centrale, which is in GIF, that's where I lived. But I did come visit Paris every weekend, so I think I can call myself an honorary Parisian. But my PhD journey was I thoroughly enjoyed during this time in France. I learned a new language. I'm originally from India, and I thought, I'm coming to Paris, I don't need French. But I really loved learning the language, and I had a very enriching personal as well as professional experience during my stay in France. Okay, now coming back to thermoacoustic instability. So what is a thermoacoustic instability? So from the name we can see there is something to do with acoustics, thermo, so there is something to do with heat, thermal, something like that. I'm going to play a video here, which was taken by my one of my PhD supervisors, Dr. Daniel Durox. Let's see if it works. So what you see here is sort of like a organ pipe, but a flame organ pipe. So there are tubes of different heights that you can see here. And then there is a very small burner with a tiny flame that we are going to introduce in each of these tubes, and let's see what happens. So just a small flame in one of the tubes. And then we hear some noise. And then in the second tube, the frequency is different. The amplitude is also a little bit different. And then again, the frequency changes. So essentially what we see here is as we introduce this flame into tubes of different lengths, you hear a different tonal noise, right? And then here we have a transparent tube, and then we are going to see a bit close-up of what happens actually to the flame. So this is a slow motion video of what is happening to the flame inside this transparent tube. And you can see that the flame is disturbed, and there is some kind of a shedding, periodic shedding of vortices that is taking place at the tip of the flame. So you see a small blob that is pinching off and then moving downstream. So if we actually look at what's happening, the flame is being unstable, and this is what we call thermoacoustic instability. So in a combustion process, you have the flow of fuel and air, and then that establishes the flame. So any flame that you have, it produces noise. Okay, you can hear it in your gas stove burner or any flame that exists, there is a noise. And then in engines, what we do is we confine the flames, right? So we put a chamber around it. So the sound waves produced by the flames gets reflected back and forth, okay? And at certain conditions, when we match the resonant frequency of the chamber, there is a very strong pressure oscillation that's going on. So when you have pressure oscillation in the chamber, that's going to affect the flow rate of fuel and air. Now when the flow rate gets affected, the flame gets affected, the sound changes, and then this process keeps happening in a loop. Okay, so this is what we call as thermoacoustic instability. So oscillations in flow rate results in oscillations in heat release rate from the flame, and when that matches with the chamber resonant frequency, the oscillations blow up. So if it is a simple flame like this, the flame itself is having a very small amount of heat release that's produced. But imagine an aircraft engine or a rocket engine. There is megawatts of power that is produced. So even like 1 to 2% contribution of this power from the flame to this phenomenon can be quite phenomenal, and there can be very strong pressure fluctuations. So this is a scaled down helicopter engine, okay? So there is an annular chamber with multiple flames, and this combustor is undergoing thermoacoustic instabilities. Now let's see what happens. So you hear this intense noise, and also sometimes some of the flames blow off, right? The flames don't exist anymore. Now, we don't want this to happen when we are flying at 32,000 feet in an aircraft. We don't want the flames blowing off. So it becomes quite challenging to understand why this happens and how can we prevent it. Why must we avoid them? So some pictures from actual engines. So here is a new burner assembly that got damaged because of thermoacoustic instabilities. And this picture is quite phenomenal. It's a rocket engine from the 1950s. And you can see that the metal chamber actually looks like torn paper. So it can structurally damage the engines because you have all these sound waves. And when that couples with resonance of some of the structural components, it can blow up these engines. So it can cause noise, as you heard it, and then it can cause blow off, you just saw it, and then it can cause mechanical failure as well. So now we are at crossroads with aviation, so we need to reduce CO2 emissions. Now actually we must reduce CO2 emissions. Either we reduce it or we don't fly, right? So now we are at this crossroad, and some of the options we have is we can either use biofuels in these engines, we can use hydrogen. Of course, there is also the option of using ammonia, but that's again a hydrogen carrier. So we have all these options, but the problem is when we introduce these new modifications, the thermoacoustic instability in these engines, it's going to change. So we need to try and understand what happens to this phenomenon when we make any changes to the engine. First, let's look at biofuels. So it's also called sustainable aviation fuels. So these are still hydrocarbon based. So they don't completely eliminate CO2 emissions, but the biofuels are derived from cooking oils, household waste, agricultural waste, and we extract these plant-based waste. We blend them with traditional jet fuel, and you have the sustainable aviation fuel. So when you use it in engine, there is still carbon dioxide emission, but because a major part of the fuel is coming from plants that has already absorbed carbon dioxide, you can have about 70% reduction in the overall emission of carbon dioxide. So the thing about SAF is we don't know what exactly will be the composition of SAF. So there are blends of, so SAF is sustainable aviation fuel. So there are blends of different components with varying composition. So what that means is one part of the fuel can burn faster compared to the other part. So the mixture is just going to have different chemical properties. So the question is, what happens to instabilities when we have a different fuel composition? So currently we only have kerosene that we use in engines, but when we start using sustainable aviation fuels, what essentially happens to thermoacoustic instabilities? So to understand this, we use this lab scale annular combustor. So this is a scaled down version of a helicopter engine combustor. So it's only the combustor, there is no compressor or turbine, just the combustor, and it has about 16 flames around it. And this is at the M2C laboratory down in Gif-Suhuet. Why do we need annular combustor? So this is an aircraft engine. This is a cut section of the engine. So there is the compressor in the front, turbine at the back, and there is a central shaft that's connecting the compressor and the turbine. So the combustor itself is placed around this shaft, so it takes an annular geometry. So if we want to actually understand what's going on in reality, then we need something that closely resembles the actual geometry. Remember, thermoacoustic instabilities, it has acoustics, so the actual geometry of the system is quite important. Just to quickly tell you the construction, it's actually quite simple. So there is this cylindrical section in metal, which is the airflow chamber. So air comes in via this section. And then there is this transparent section that you see downstream. that's the combustion chamber. So this is where the flame exists. And in between the two, so there is the cylindrical airflow chamber, cylindrical flame chamber. In realistic configuration, that is in actual engines, this is not transparent, but in lab scale, we want this to be optically accessible so we can look at what's happening to the flame. And then there are these small sections in brass that you see here, 16 of them, that actually holds the flame. So there is a blown up version of this injector section. So air comes in from the airflow chamber, it comes to the air distributor. And then there is a swirler. So what the swirler does is it gives a rotational motion to the incoming airflow. And then there is the liquid fuel atomizer. So typically we use liquid fuels, and kerosene is liquid. So there is a liquid fuel atomizer. And what this does is it produces fine droplets of fuel spray. Okay? And you have fine droplets, then it can vaporize more easily. And then we want it to mix with air for a good combustion to take place. So the swirler, imparting the rotational motion, helps mix the fuel and airflow well. And then it exits through this terminal plate that has a conical section, and then the flame gets stabilized just downstream of this injector section. So in order to understand what happens to the thermoacoustic instability, we looked at the stability map of this annular combustor at different operating conditions. So just like a whole operating envelope of the combustor. So we varied the thermal power and the equivalence ratio. So when I say equivalence ratio, it's just how much of fuel we are using with respect to the air. And then we consider all these red dots at which we carried out the actual experiment. So these are the operating points at which we did the experiments to get the instability in the whole operating map of this combustor. Okay, so we considered three fuels. Okay, gaseous fuel, propane, a volatile liquid fuel, heptane, and another fuel, dodecane, which is very close in properties to kerosene. Okay, so with respect to a gaseous fuel, we don't have to atomize or vaporize it. It is already mixed with the air. Okay, so it can, as soon as it enters the combustion chamber, it can burn. With heptane, which is a volatile fuel, and a liquid fuel, we still need to atomize it. So we need to produce very fine droplets of heptane. So there is some extra time that it requires before it burns. So it's called the atomization time delay. And then when we have, but then because it's volatile, it's going to vaporize right away. So it doesn't need time for vaporization. As soon as it atomizes, it can burn. And then there is the third fuel, which is dodecane. It's not a volatile fuel. So we'll have to first atomize it, and then it vaporizes, and then it burns. So it sort of takes a longer period of time before it burns compared to heptane and propane. So what we are essentially trying to do here is tweak the time delay for combustion and then see what it does to the instability. So here is the stability map first with propane. So as I mentioned, propane is gas. It has the smallest time delay for combustion. So the x-axis has thermal power, y-axis has equivalence ratio. And what you see here in the map is the amplitude of instability. Okay, I missed to mention it, but in the annular combustor, we have microphones at different locations, and that captures the pressure fluctuations in the chamber. So it measures how much is the acoustic pressure amplitude. Okay, so as we go from blue to green to yellow to red, okay, we go up in the amplitude of instability. So if it is blue region, then our combustor is not undergoing any thermoacoustic instability. Red is the highest amplitude of thermoacoustic instability. Okay, so what we can see with propane is there are very few blue regions, so the combustor is mostly stable, and in this zone it is really unstable. And then with heptane, now we start to see some blue regions. So there are more operating points that are stable, but then there is still this big zone of yellow and red where the combustor is unstable. And then the third case with dodecane, which is similar to kerosene, where you have a lot of blue regions. So the combustor is stable at a lot more operating conditions. So the question is, so what is essentially causing these differences between the three fuels? In order to study this, we need to look at the flame, because the flame is the source for the thermoacoustic instability to take place, right? So we want to study the flame, and it's just harder to do experiments in the full annular combustor. We still need it to understand what is going on, but it's just harder to diagnose what is going on. So we took one injector from the annular combustor and then made another setup, which is the single flame configuration. So it's just one injection unit of the same dimensions, and then we see what the flame is, what is happening to the flame with the different fuels. So in order to study that, we have a camera. So this camera is looking at a certain radical emission from the flame. So what's so special about this excited OH star radical is that emits at 310 nanometers, which is ultraviolet, we can't see it with our eyes, is that it is well known to be the measure of heat release from the flames. So experimentally, we can't measure the heat release, but the proxy for heat release is OH star emission. So that tells us what's happening to the heat release, which is the source term for thermoacoustic instability. Okay? So we use an intensified camera, we put an optical filter, and the optical filter only lets the emission around 310 nanometer to be captured by the camera. Okay? And so we do this, and then we have the three different flame shapes with the three fuels. So you see yellow and red regions, but these are false colors. The flame doesn't look yellow and red, but again we are capturing in ultraviolet, right? So we just put some color to it in order to properly visualize the flame. So first with propane, you see that the flame takes an M shape, and then we go to heptane. It's still an M shape, but then you start to see that the central portion is a little bit different compared to propane. And then we go to dodecane. Now the flame is open, and there is pretty much nothing that we see at the center. Okay, so what we see here is, yeah, there are some differences in the flame topology, but how is that affecting thermoacoustic instabilities? So in the annular combustor, I told you about this coupling between combustion and acoustics, right? So this is a feedback process, okay? And in the single injector combustor, what we tried to do was decouple this feedback loop, okay? But we still want to have the flow oscillations that takes place in order to understand what is happening to the flame, okay? So we decouple the feedback loop, and what we do is we put some loudspeakers, okay? Now these loudspeakers can oscillate the flow, okay? But we have more control over what the loudspeaker does. We can choose the frequency, we can choose the amplitude at which it operates, okay? And when there is, so we choose what the loudspeaker does to the flow, and then the flame gets affected correspondingly, and then we try and understand what's happening at different acoustic frequency and amplitude. So that's the idea of using this single flame configuration. So no feedback loop here. We externally force the flame to see what is happening. So when we do this, we can get some sort of a transfer function for the flame. So when I say transfer function, it's nothing but we give a certain input and then we see what's happening to the output. So in our case, the input is flow perturbations. So I've denoted it by U, so the velocity perturbations. And then the output is Q, which is the heat release rate perturbations. Okay? So the transfer function, so transfer function is a linear concept. We can also give another fancy name describing function, which is just a nonlinear extension. But at the base, it is just relating input to output. Okay? So F, which is the flame describing function, relates the output heat release rate fluctuations to the input velocity fluctuations. Now this is a complex quantity, so it has a gain, which is the amplitude, and a phase phi, which tells us about how delayed the process is. Okay? Now we can use a lot of different experimental techniques to measure heat release rate and velocity fluctuations. So for heat release, we can use a camera. We just spoke about the chemiluminescence from the flame. And then similarly, velocity, we can use a particle image velocimetry or a lot of different techniques. Not that these are easy, they are quite hard to do in reality, but then there are several techniques that are available. So here is the stability map with the three fuels, so propane, heptane, and dodecane that we saw earlier, and the change in the flame shapes that we also saw. Now let's look at the the flame describing function. So as I said, it's a complex number, so there is a gain and there is a phase. Okay, so top row for propane, then heptane, and then dodecane. Okay, if we first, so you see that the x-axis is at different frequencies. So these are the acoustic frequencies with which we are forcing with the loudspeaker, and then on the y-axis here you have the gain, and here you have the phase. Okay, so if we first consider propane, that has a very high gain. Okay, a higher gain means typically higher amplitude, and then when we go to heptane, it is slightly lower, and then with dodecane, it is much lower than the other two cases. Then there is the phase curve. Okay, so with the phase curve, with the slope of the phase curve, we can also obtain a time lag. So what is this time lag? It's the time taken for the velocity perturbations to reach the flame. Okay, so how delayed is the change that we are making, taking the time to reach the actual flame. Okay, so with propane we have a smaller slope, which means a lower time lag, and then as we change to heptane to dodecane, the slope increases, which means the time lag is increasing. So this sort of makes logical sense, because you remember I told you propane is a gas, right? There is no atomization or vaporization time delay. So we do expect a smaller time for the combustion to take place. With heptane, we have introduced atomization time delay. There is not much vaporization time delay. And then with dodecane, we have a lot more time delays. We have to atomize the fuel, vaporize, then mix it with the air before we burn. So we are sort of starting to see some patterns in terms of the gain tendency as well as the phase tendency. Now, we can define a low order model, but I'm going to put it in very simplistic terms. So in the 1700s, Lord Rayleigh was the first person to discover this phenomenon. And he proposed a very simple criterion. No? Only when the pressure and heat release fluctuations are going to be in phase, so acoustic pressure and heat release are going to be in phase, the oscillations will happen. If they are out of phase, they are just going to cancel each other, and they are not going to, there is going to be no feedback loop at all. So Rayleigh criterion says in phase oscillations between pressure and heat release. Very straightforward, very, very logical, nothing too complicated. Then based on that criterion, we can define some instability bands. Okay, so phi is the phase of the flame describing function. Okay, and based on this in phase oscillation criteria, can define another criteria. So if the phase is between pi by 2 and 3 pi by 2, then we will have instability happening. But if it is outside of this limit, there is going to be no instability. Just to show you an example, so this is a sample phase curve. The gray region is this band. When the phase is inside this band, it is unstable. If it is outside this band, it's going to be stable. Okay, so while I say this very simply, we have a complicated equation to arrive at this. We have to write down the acoustic wave equation. Then there is a source term here, which is the flame, which we represent using our complex quantity flame describing function. And then we solve for the dispersion relation. And then the phase of the FDF will tell us whether the combustor is stable or unstable. And the gain will tell us how much is going to be the amplitude of instability. Okay? So let's forget about this. Let's not go much detail into how the modeling is done. So with this dispersion relation, we can come up with this instability band. Okay. Now I've put the phase curves for the three fuels. So red is propane, blue is heptane, and green is dodecane. Okay. I've chosen one point on the stability map. Okay. And the frequency at which this instability occurs is around 750 Hertz. So that's what is marked as the black dotted line. Then if we see for propane, this point lies within the gray band, which is the instability band. Okay, so we expect the combustor to be unstable. With heptane as well, it's inside the band. So again, it has to be unstable. But for dodecane, it is outside the band. So we expect it to be stable. Okay, does that correspond to what we see in reality? With propane, it's in the yellow or red region. So that's unstable point, and the model correctly predicts it. For heptane as well, the unstable point, the model correctly predicts it. And then for dodecane, it's in the blue region, outside the band, so it's a stable operation. Okay, so essentially what this shows is, if we want to understand whether our actual engine is going to be stable or unstable, we don't have to do testing with the actual engine because that's expensive. Rather, we can just take a single flame from this combustor and then study it, use this model to predict the instability. Okay, so that will save a lot of time and cost. Okay, so now we have looked at what happens when we consider a biofuel or something that mimics a biofuel kind of configuration. Now let's go to hydrogen, because hydrogen is a newer fuel. We haven't done a lot of studies with hydrogen. So what's good about hydrogen? There is no carbon in hydrogen, so no carbon dioxide. Of course, there are other pollutants, but at least carbon dioxide is not going to be there. But the challenge with hydrogen is it's highly reactive. So what that means is, if we mix fuel and if we mix air and hydrogen, it can actually even sometimes spontaneously burn when the temperature is high enough. So if we pre-mix air and hydrogen, what that's going to cause is create flame in our engine where we don't want it. For example, in the mixing chamber, that's not where we want our flame. We want it in the combustion chamber. Okay, then let's go non-premixed. What happens if we don't premix? Then what might happen is the air and hydrogen may not mix well, and that can sort of increase the oxides of nitrogen that is produced, which is another pollutant that we don't want. So what we need with hydrogen is a way to quickly mix, like partial mixing, something that's in between the two modes, so we can avoid flashback as well as lower oxides of nitrogen. Okay, and one potential configuration for that is jet and crossflow. Okay, it's a configuration that's used in a lot of other applications, not in combustion, for example, cooling. And what essentially the configuration is, so there is a cross flow of air, and then we inject high velocity hydrogen jet perpendicular to it. So essentially there is air and then high velocity hydrogen jet coming, it pierces through the airflow, and in the process it mixes. Okay, so that way we can have quick mixing and stabilize a flame. So here we are not going to look at a complicated annular combustor. We are going to look at a very simple case, simply because we haven't fully understood thermoacoustic instabilities in hydrogen. So the configuration is actually quite simple. So there is a square cross-section chamber. So this is air comes from the bottom, and then inside this optically accessible or the transparent section, we inject hydrogen, and depending upon how we want it, we can have one hydrogen jet or multiple hydrogen jets, and the flame gets stabilized here. Okay, if we are to think of using hydrogen in aircraft engines, then we need multiple jets. So if we study multiple jets, that also tells us, is there flames interacting or are they separate, and it can give more information. So again, we are going to, so this is that chamber that I showed you. Hydrogen is injected and the flame is stabilized. We are going to use a high-speed camera, again looking at the OH radical emission. Okay, so heat released. So if we can look at the flame in different views. If we look at the front view of the flame, we see a U shape. Then this is the side view, which is what we see here. So this is the injection wall, and the flame sits at the point where it is injected. Okay, and just to tell you with respect to this, air is coming in this direction, so from the bottom, least from the top. Okay, so we use this high-speed camera with the optical filter, and then take 4,000 frames per second. Okay, quite a lot of frames. So what this gives us is both spatial as well as temporal information. So because we are using a camera, we get spatial information, and because we are doing a high-speed acquisition, so looking at the flame at a like capturing a lot of frames per second, we also have some temporal information that we can get. And then we can use like a smart data analysis technique called proper orthogonal decomposition. You might have heard about it. So it's essentially a way to identify oscillatory modes. Okay, So just in simple terms, what we do is we have high-speed camera. So there is certain pixels, so some spatial dimension, and then we have a number of images. So in this case, we have 4,000 images per second. Then what we do is we create a data matrix. So we squish the pixels into a single column, and then have multiple images in each column. Okay, we just arrange the data in a certain way, and then we do a mathematical operation called singular value decomposition. Okay, essentially that's just pattern extraction. We are looking for patterns in the flame or in the flow. Okay, and then when we do this, we get the different oscillatory modes. So for example, the first mode, second mode, third mode, and as we increase the mode number, the energy decreases. Okay, so let's say there is an 100th mode. It will have very low energy, and essentially what that means is it's not a physical mode, it's just a mathematical mode. So we need to be careful in only looking at modes that have high energy to make physical sense of what's going on. So here are some sample modes. So this is the side view imaging that we are looking at. Mode 1, we are not going to discuss much because it's just the mean image that has the highest energy. And then we will look from mode 2 to mode 5, and anything more than mode 5 we will not see because those are low energy modes, and we cannot distinguish whether they are physical or mathematical. So like I said, we are looking at the side view of the flame. Okay, so let's look at these two modes. So the red and blue color, what it shows is these are the oscillatory patterns that you have. So the flame essentially moves from red to blue. Okay, so if you see these two cases, the flame boundary goes towards the wall and away from the wall, towards the wall and away from the wall. That's what these two modes show us. Okay, so these are just from the spatial information that the camera has provided us. We can also use the temporal information and do a fast Fourier transform, and that's what we have here. So this is the frequency spectrum. Okay, and what we see here on the frequency spectrum is a peak at 240 hertz. Now where is this coming from? So I told you about this chamber, right? A very simple setup. We can do an idealization of this chamber. Consider one end is closed, one end is open, and then there is a flame, and what that flame does is it changes the temperature from a cold temperature to a hot temperature. Okay, if we do this simple modeling and then find out about the first acoustic mode of this chamber, that exactly comes to 240 hertz. Okay, so these two modes correspond to the first acoustic mode of the chamber, the first resonant mode of the chamber. Okay, so this is our cross flow tube. Okay, what's happening is the airflow is moving up and down. Okay, so that's what is happening at 240. This is happening at 240 hertz. So the flame is sort of going up and down. That's what you see in these two modes. And because it's of this shape, it looks like it's going towards and away from the wall. Okay, it's just up and down movement of the flame. Okay, now let's go to mode 4. You start to see staggered patterns, right? So there is red blue, so the flame moves like this, but then there is also red blue like this, so it moves along the boundary, some sort of like a snake-like mode. So there is some wrinkling going on, and if we look at the fast Fourier transform, the frequency spectrum, then we see two frequencies, 240 hertz, which is our first resonant frequency of the chamber. There is another one at 720 hertz, which is the second harmonic. Okay, so what's going on here is we already saw our cross flow fluctuation, so the airflow is going up and down, but that's not the only thing, right? There is also the injection tube. So when there is pressure fluctuation here in this tube, the flow that's coming perpendicular is also going to respond to these fluctuations. Okay, so now this causes towards and away from the wall motion, and then this causes these staggered patterns. Then we can also look at the front view. The front view of the flame looks like a U shape. Then what we start to see here is something we haven't seen on the side view. So these are the two flame wings, and then we start to see that these flame wings move in the transverse direction. So essentially what's happening is they are going like this, they are oscillating like this. There is a synchronous oscillation of the flame wing, so when this side goes to the right, this side also goes to the right. So blue, blue, red, red, right? So there is this oscillation that's going on. We can't see it in the side view because this is out of plane oscillation. So only with the front view we will be able to see this. The next one, this one is the U going up and down. That's just what we saw here, towards and away from the wall, that manifests as, it's just an up and down motion of the flame. This is the staggered pattern that we saw before. Okay, good. So we start to see some oscillatory modes with a single flame. Now we can also see what happens if we have multiple flames. Okay, so we have 3 flames, so 3 hydrogen jets that are injected, stabilizing 3 flames. So in the front view we see 3 U's. Previously we saw only 1 U-shaped flame. Now because of 3 injection points that we have, we see 3 flames. The side view, 1 flame is behind the other, so there is no difference. We don't see anything different on the side view. Each flame is behind the other. So because the side view looks the same, the modes between the multiple flame case and the single flame case shows no difference in the oscillatory patterns. Exactly the same modes that we see. The frequency spectrum also shows the same frequencies. But something interesting happens in the front view. Okay. Now let's look at the first case. So 3 flames. Again we have these alternating patterns. The first one, the flame wings move synchronously. So all 3 of them are moving like this. They behave in a synchronous fashion, just like the single flame case where we had the synchronous pattern. Okay. This resembles something, another physical system. Let's think of a couple pendulum system. So we have 3 pendulum connected by a spring. Okay. If we write down the equations for this and then solve for the wave equation, the first mode that will come out of this is a synchronous oscillation. So all 3 masses will move in the same direction. Okay. So our flames, a completely different physical system, is behaving like a couple pendulum system. Now let's go to the third mode. Okay. So you don't see a lot of motion of the central flame, but the 2 side flames move. Okay, you see alternate red and blue patterns. But what is interesting is they don't move synchronously anymore. So for example, if the blue here, when there is blue here, there is red here, which means the flames are moving like this. The central flame is just staying in its place, and the side flames are moving anti-synchronously. Okay. We didn't observe this in the single case. If you remember, there was only the synchronous oscillation. So again, going back to our couple pendulum case, when we look at the second mode of the couple pendulum, the central mass doesn't move, but the 2 side masses move anti-synchronously. So it's exactly resembling the behavior of a couple pendulum system. And another interesting thing is we also see something going on, some action going on downstream. So what is this? If you see this video, sometimes you can notice that the flames interact, like for now, and then there is a blob of flame because of this interaction that is convected downstream. Okay, so this unsteady motion is causing another unsteady pocket of flame that's formed and then convected downstream. Now imagine we put a turbine here, and when this takes place, the turbine is going to see different heat loads, and the turbines are not designed for that. So this anti-synchronous oscillation also produces unstable flame pockets downstream. Now let's go to mode 4. The left flame is not moving, but the central and the right flame is moving. Again, so when there is red here, there is blue here, so it's moving anti-synchronously. Okay, so the left flame is the same, but the central and the right flames are moving like this. Okay. So because of the anti-synchronous motion, again you see some flame pockets produced downstream. Now if you look at the fifth mode, this flame is not moving much, but these two flames are moving, and again anti-synchronously. Okay, so in this case the left flame did not move, in this case the right flame did not move, and these two combined together resembles the third mode for the couple pendulum system. Okay, where you have the left and the right moving synchronously, but the central moving anti-synchronously. Okay, so it's just profound how these flames actually behave like a couple pendulum system. So that means this couple pendulum is already solved for, so we can use the exact equations to understand and predict the instabilities of multiple hydrogen flames. These kind of instabilities have not been previously observed with hydrocarbon flames. Only with hydrogen this sort of couple behavior is starting to show up. Okay, now let's go to, okay, we understand that thermoacoustic instabilities are a problem. We sort of know how to detect them. Now we want to control them. We don't want it in our engines. We can adopt two strategies. We can go for a passive strategy and an active strategy. Okay, so in a passive strategy what we do is, okay, we see that there is instability and then we make some changes to the system. Okay, so for example, if it is an actual engine, okay, there is an instability, let's stop the engine, let's make some changes, and then let's see if the instability is present or not. That's the passive approach. In an active approach, as soon as we detect the instability, there is an active change that you make to the engine to solve for the, to suppress the instabilities as and when it is happening. So you don't have to stop the engine, but you sort of have an adaptive way to suppress the instability. So there are two approaches that we can take. So I'll give an example of a passive approach that we used. So I said there is the liquid fuel that is injected, right? What we can do is we can change the way the fuel is injected. So here you see three different spray profiles. Okay, so a lot of, it's a very dense spray. Now it's not, there's not much at the center, there is nothing at the center. So when we change these spray profiles, it obviously affects the flame. Okay, so you have different flame topology, and that clearly affects the gain and the phase of the flame describing function. Okay, now this configuration corresponds to a lower gain, a narrow instability range, which means we'll have lesser possibility of this flame going unstable compared to this flame, which has a very high gain. Okay, so this is one way to suppress instabilities in a passive way. The other thing that we can do is we can change this element. So we can change the swirler. Okay, how much rotational motion are we imparting to our airflow? That's another thing that we can change. So here we have a lower swirl with a stability map that's actually stable through the whole of the operating envelope, and a medium swirl and a higher swirl, which we start to see more and more unstable points. And we change the swirler, again the idea is we change the flame topology, and then with this flame topology we have a very low gain, and that's why we have all operating points to be stable. Okay, and then as we increase the gain, we start to see more unstable operating points. So this is a passive approach. Is this a smart approach? As we transition towards decarbonization, we are going to use different fuels. Especially in the current context, we don't want to be geographically reliant upon one part of the world to have our fuel. Okay, for example, we could have more hydrogen produced in France or in the UK, and then there is more agricultural waste available in India, and we could switch to biofuels there. But we don't want to keep reinventing our engine. We want the same engine to use different fuels. So we want our engines to be fuel flexible. If they are fuel flexible, then we don't have time for passive control. We can't be like, let me not operate my aircraft engine for 1 year, let me figure out how to solve instability in India, and then I'll come back to the UK and then reinvent the wheel and solve instabilities with hydrogen. So we don't want to do that. We want, as we progress towards the future and we want decarbonized engines, active control is the way to go. So one of the ways in which we are trying to do this is using plasmas. So what are plasmas? High voltage electric pulses. So we apply, these are the electrodes, there is a small gap between them, and we produce, we pass high voltage between these two electrodes and produce a plasma. So we just break down air or fuel, and that can help in 3 different ways. It can break down species in air and fuel and produce favorable species that we need for combustion. It can locally increase the temperature of reactants, can also alter the flow regime. So there are different ways in which plasma can be really helpful. And then here is an unstable flame. Then as soon as we turn on the plasma, it stabilizes. Okay, so the idea is we have a combustor, and then as soon as we detect the instability, we have an active control algorithm. So we can use different ways to build this active control algorithm. We can have a database of flame transfer function with different fuels. So there is a lookup table, or we can use some AI-based models that feed into this active control algorithm. And as soon as there is an instability, the algorithm tells the plasma to be turned on. Okay? And when the plasma is turned on, can have our flame go from unstable to stable. Okay? So this is an active control approach that we are currently trying on, and hopefully this can help with fuel flexible engines. Okay, so just some key takeaways. What we saw is new fuels means different ways of triggering thermoacoustic instabilities. With biofuels which have widely varying composition, we noticed that with the cases that we considered, the instability boundaries and amplitude changes, and it's primarily coming from the change in flame topology. And then we can develop a low order model based on flame describing function in order to predict what will happen to instability in actual engine. So we don't have to work with actual engine, but we can use a simplified configuration to predict the instability. And then with hydrogen, we saw that new modes are triggered. So we saw that with a single jet and crossflow case, on the side view we had some elbow oscillations and then wrinkle oscillations, and in the front view we saw synchronous flame oscillations. But when we moved to a multiple jet and crossflow case with hydrogen, we started seeing new modes. So in addition to the synchronous mode, we had anti-synchronous modes, and the anti-synchronous modes produced more unstable flame pockets. But the good thing is they are analogous to a coupled pendulum system, so we can use the coupled pendulum system as a strategy to model these flames. Then also we looked at control techniques, so we can use passive control. Passive control is detecting the instability and then making the changes. We can modify the liquid fuel spray, we can modify the swirler, which again changes the flame topology, and that way we control the instabilities. But a smarter way to go about it is using active control, which can help with fuel flexible engines. So that's the one way we saw it is using plasmas, and then adapting the flame topology as and when instability happens to suppress it. So thank you so much. I hope it was not too intense and it was clear enough. If you have some questions, I'll be happy to take it.
Few questions.
Thank you for your presentation. Do you think it would be feasible to retrofit current engines with the active control of a plasma in a very high temperature and high pressure environment as in the combustion chamber?
So that's what we have to eventually do. We don't want to come up with newer and newer engine architectures, but this active control method is only in the fundamental stages. So we don't fully know how plasma or when plasma can suppress instabilities, and where exactly we have to place it in the combustion chamber to suppress instabilities. There is also plasma also requires energy. So are we making sense in terms of using so much amount of energy to suppress instabilities? So it's in a very fundamental stage, and these are the sort of questions that I'm trying to look at through this project.
Hi, thank you for your talk. So I have a naive question maybe, but the experiments you ran when done in a lab with a density of about, let's say, sea level, a plane flying at cruise altitude has a density at the combustion chamber of around 5-6 times that.
Yeah.
How would you expect it to affect the instabilities you're observing?
Yeah, so it's a very valid question. The instabilities can change with pressure, but the good thing is we now have a strategy on how to tackle it, right? Because we know that if we use a simpler configuration at pressure, that translate to an actual pressure operating, actual engine operating at pressure. So the studies that sort of we have identified, for example, with the biofuel work, gives us a framework that we can use to predict instabilities of an actual engine which is at pressure. With hydrogen, everything is new, so we have to also see if the same sort of coupled behavior happens with pressure, or does it change in a different way. So these are the things that are still yet to be explored, because with hydrogen we don't understand much really. We know it burns, but what happens with respect to thermoacoustic instabilities is something that we are yet to understand. So yeah, the next way to go forward will be to study it at pressure and then see if we can use the same sort of modeling approach at pressure as well.
Thank you for the talk. It was very clear. Concerning the analogy with the coupled pendulum, do you have any idea of either simple analytical modeling or numerical modeling to identify the parameter of this model, like the equivalent masses and stiffnesses, so the coupling factors between the flames?
Yeah, so that's the idea. That, I mean, it's still ongoing work. It resembles a coupled pendulum system. So that's good, because instead of, if we have 5 flames instead of 3 flames, then we can have 5 mass coupled pendulum system and then exactly model it. But one of the question is, what is the pendulum, what is the mass in case of a flame, and what is the spring? I mean, we know that between the flames or between the jets, there are some vortices that are interacting. That's probably the spring, but we still have to study it and then see what is exactly the mass and what is exactly the spring in case of the different flames. Yeah.
Any more questions? Yes. Question from next slide.
Thanks for this nice talk. I just wanted to know, in your slide 20, when you have your network model,
Yeah.
when you guess that for this point 700 Hertz is the frequency that you target, is an output of your model, or it's an input for your prediction?
Yeah, so essentially it's sort of, we can do it at any frequency. Here I have chosen 750 Hertz, just at this point. So we have already done the measurement here and we know this point is at 750 Hertz, but it could be at 700 Hertz as well. It could be at 800 Hertz. So essentially the reason why we have this loudspeaker doing it at different frequencies is so we can pick and choose the frequency and see whether the combustor will be stable or unstable at that particular frequency. So for example, if we choose this frequency, let's say 400 Hertz, then heptane is going to be stable, propane is going to be unstable, dodecane is going to be unstable.
Okay, one more question.
Thank you. On the same slide, perhaps I missed it and sorry for that, but how do you relate the frequency that you choose at the left to the parameters at the right, thermal power and equivalent ratio? Did you just measure the frequencies at the black dots?
Yeah. So I told very briefly that we have different pressure sensors in the chamber. So we can get both amplitude as well as frequency. So when you do a fast Fourier transform of the pressure signals, we can get an equivalent frequency. So this is, I mean, this I showed it as a demonstration of how we can use the model. But in reality, we don't have this. This is what we don't have. This is what we have. So what we can do is we can actually know at what frequencies the combustor will be stable and at what frequencies the combustor will be unstable. And that way we can reconstruct this map. So here I showed this map just to tell you that actually this is a validated model. And in reality, we don't have this, we only know this, and then we can find out at which exact frequency is our combustor going to be unstable.
Thank you.
Another one?
your talk. I had a question about the plasma effect, because as you said, in the end, when we had a plasma, we increase temperature, we create very reactive radicals.
Yeah.
But considering the frequency, shall we understand that adding a plasma, I don't know, decrease the frequency of the oscillation, and that's why you go into a stable configuration, or?
So essentially, again, the effect of plasma is to change the flame topology. Now, so if you see in this picture, the plasma is here and the flame is downstream of the plasma, but I can also put the plasma downstream of the flame. Okay, that will change that will make the flame shape to be in a different way. Plasma doesn't have to necessarily suppress instabilities. It can also amplify instabilities depending on where it is located. We know these are the effects that are caused by plasma, but are these favorable for suppressing instabilities or not is something that needs to be explored and understood.
One more, just before noon. Yes? No? Okay, no. Thanks again.
Thank you.